These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There is a link to my website in the info box. The address is www.freelance-teacher.com/videos.htm, or you can just use the link in the info box. By the way, I also offer tutoring via Skype, and you can find more information about that Skype tutoring service at my website. Thanks. Question 31, hexene plus hydrogen bromide, and also hexene plus hydrogen bromide and peroxide. So let's try drawing the products and or the mechanisms from that. Hi.
One doing it with HBr and the other one with HBr.
Oh, okay.
So the difference is depending where you want the BR, if you want it on the more substituted or least substituted.
That's the difference. It's a regiochemistry difference. Regiochemistry is when there's more than one region in the molecule where the reaction might take place. So the whole thing this is testing is whether we're going to end up with Markovnikov or anti-Markovnikov, whether the bromine is going to end up on the more or the less substituted carbon. Well, it looks like a lot of you made some good progress on these reactions, especially a lot of you got the mechanism right for the radical mechanism, which is good because this is a complicated mechanism. If you're still shaky on the mechanism, I think I put it on the board here again. It's complicated because there's two initiation steps. First, the peroxides split up to make a peroxide radical, and then the peroxide steals a hydrogen to make the bromine radical. So these two together are the initiation. And then there's two propagation steps. First the bromine joins, and then the hydrogen joins over here. Okay, and the key difference between these is notice that in the radical mechanism, the bromine joins the alkene first. That's why it ends up on the less substituted carbon, because it wants to form the more substituted radical, where the hydrogen ends up. Whereas in the electrophilic addition model without the peroxides, the bromine adds second. So it ends up on the more substituted carbon, because that was the more substituted carbocation. That explains the difference. So this first reaction, would we call this Markovnikov or anti-Markovnikov? The first reaction was the Markovnikov, because the electronegative atom ended up on the more substituted carbon. And then the second reaction was anti-Markovnikov, because the electronegative atom ended up in the less substituted carbon, and we can explain that with the mechanism. So this is a distinction you're pretty sure to see tested on the exam. One thing to review, we always want to ask why electron pushing arrows are reasonable. Why is it reasonable for this double bond here to be at the tail of this arrow?
Because it's a nucleophile.
Yeah, and how do we know? Because we just have memorized that carbon-carbon pi bonds can be nucleophiles. And why is it reasonable for this hydrogen to be at the head?
It's slightly positive.
It's got a delta positive and a good leaving group, so that makes that reasonable. Obviously, this reaction is reasonable because we have a negative attacking a positive. Now, one thing that I think some of you got and some of you might not have gotten was, let's see, when the hydrogen attacks this carbon over here, did this form a stereocenter?
No.
No. However, when the bromine attacks this carbon, did that form a stereocenter?
Yes.
Yes, so it was important to show the two different products. So some of you got that, which was good, and maybe some of you missed that. So the two different products. The bromine can either attack from in front or from behind. So the bromine should end up either on a wedge or on a dash on this carbon. We always have to ask if we're forming a stereocenter. We've got to get in the habit of asking if we're forming a stereocenter. So these would be the two different products from the electrophilic addition. How about in the second reaction? Let's see. Was this a stereocenter?
No.
No. And was this a stereocenter?
No.
No, so we didn't need to worry about multiple products there. By the way, in terms of terminology, this is called electrophilic addition because it's initiated by the electrophilic hydrogen attacking. And the second reaction is called radical addition for the obvious reason that it's a radical mechanism.
Okay.
That's the deal.
Is it different when it's with like cycloalkenes, or should we just move on?
Let's see, so the basic idea is the same in all of these cases. The idea in all of these cases is that in the electrophilic addition, you'll get the Markovnikov product, and in the radical addition, you'll get the anti-Markovnikov product, if there's a difference between them. For example, cyclohexene, I think both carbons have the same amount of substitution, so there's no distinction between those. But yeah, it doesn't really matter whether you're attacking something cyclic or not. I don't think that should give us any new issues.